Okay, the best way to learn about how to use a program like this is to just watch it being used. So I've got this data for a customer that wants a pipe designed. So let's just get started. Bottom left, you can see there's 4 sheets. If you click on the tab, you go to the sheet. Sheet 1 is for the basic data, and here's the pipe section lengths right here. Bore stroke, uh, header length. Sheet 2 is for this section right here is for the diffuser, and then right here is for the baffle. And you can see it's set on automatic right here, so that's good. And for the diffuser, it's set on manual, so I'm going to put an X for automatic and delete the X for manual. So then whatever length of diffuser and baffle that is right here, either put in manually or calculated by the program, will automatically be calculated here, and then these special calculation numbers will pass on to sheet 3, and sheet 3 will use that to create the return waves. This is the return diffuser wave, this is the return baffle wave, this is the trailing wave from the exhaust pulse, and below it right here is the pipe power band. This red being the trapping of the baffle return wave at the exhaust, and this green is the intake power. Well, the boost from the intake due to the diffuser wave, and the two are calculated together to get this blue graph right here, which represents the pipe power band. This is not the total power of the engine. This is the pipe power band. This is what is put on top of the engine power to pull it up for those 2,000 RPM. On sheet 4, right here is the data for the widths of the exhaust port from the top to the bottom. Every 1 millimeter down, what is the width? And right now I'm going to get started on that, and I'm going to pause the video to do it. Okay, I just finished entering these numbers right here, and so now if you know the port durations, you can enter the exhaust port duration right here. In this case it's 190, and the transfer port duration right here. In my case it's 126. And if you don't know the distance from the port top to the TDC point on the cylinder, which is where the top edge of the piston is at TDC, then you get really close by looking at this this chart right here. But you have to enter in the conrod length, and if you don't know what it is, just you'll be close enough just multiplying the stroke by 2. So in this case it's close to 100, so I'm just going to put 100 in. And for 190 it says 19 above port, so I'm going to put that 19 right here. And for the transfers, 126 is just a little bit above 125. So I'm going to put I'm going to put 29 right here. This can be left as is. This is the transfer width right here, which is all the side transfers added together, and then half the width of the boost added in. And in this case, it's 67 millimeters. All the distances in millimeters on this program. And this right here is for if you wanted to calculate the port widths. If you don't want to measure that, and you know it's a 3-port, you know it's a 2-port, whatever, this will get you close. But I really prefer that you measure it. So if you're not going to have automatically calculate this, then this input right here is not important. And here's the compression ratio. I'm not sure what this bike has. I'm just going to leave it at 7. So now I'm going to scroll down and then scroll over to see the graph right here. When I click the calculate button, it's going to graph the two graphs here. The blue graph, where it crosses the 1.0 line, is the peak power RPM of the bare motor. By bare, I mean just due to the porting, without considering what the expansion chamber is going to add into this situation. And the red line, when it crosses 1.0, is the RPM at which the exhaust pressure goes to 0 right when the transfer port's open. So in this case, it's happening about 6,400, and above that, it's going to start infringing on the transfer. Okay. And the idea being that those two should cross very close to the same RPM. And you can raise the red graph by raising the exhaust port, and you can raise the blue graph mostly by raising the transfer ports. And well, also the red port, you can also widen the exhaust port. So I'm going to click the calculate button and see what it does. Okay. It's crossing beyond the 9,000. So I'm going to go back to sheet 1 and increase that RPM, because it looks to me like it's going to cross probably about 1,000 more, probably about 10,000. $10,500 is what I entered. Calculate it again. Okay, so it crosses right here, which is right about 9,800. Okay. Now the idea being, looking at this peak power RPM, is that if you're designing from scratch, you know, you got an engine and you just want it to be the best it can be, okay? So you port it to the max, you find it the peak power RPM, and then what you want, you've got this power RPM, power, you've got this power band right here in blue. And the peak power RPM of the engine should be about halfway there, okay? If you want a broad power band, you want it to be over here near the beginning, okay? So since these are usually about 2,000 RPM long, that 9,800, we'll just call it 10,000, so this should end like at about 11,000. So, but this is all wrong because we haven't done anything on sheet 1. I'm just trying to explain. I'm just getting ahead of myself. Okay, so let's enter into the bore and stroke, which is 50 and 48. He hasn't told me what the header size is, so I'm just going to enter in the ideal, which is listed right here as 28. Straight header. If it's a flared header, the end of the flared header would, its diameter would be right here. This maximum belly diameter comes from sheet 4, which I've already done sheet 4, so I'm going to go by this. And it says a typical max would be 79, so I'm just going to make this 80. Make it a little bit more, 85. This says the ideal stinger diameter is 10.5. Assuming he's going to make his own stinger. Otherwise, you have to go by stinger diameters that are commonly available, which are listed right here, which would be 10.1. would be the closest. Okay, typical header diameter, wall thickness is 1.5 millimeters. Wall thickness of the pipe itself, the 22 gauge is 0.8 millimeters. And in South America, typically what's available is 0.7 millimeters. So let's put in 3 diffuser cones for a reed valve. Oh, I'm sorry. He said this was a piston port. Piston ports aren't picky. It's easier to make a one cone diffuser than a 3 cones. Let's do that. This is Y for ignition, CDI with ignition curve, which advances up to about 3,000 or 4,000 and then retards the timing past that. Reed valve, yes or no? In this case, no. Most people can leave this as it is, 600 degrees at 150 millimeters from piston at 10,000 RPM. But if you use some measuring device to measure the exhaust gas temperature and you find it's different than this, then you would enter the appropriate numbers there. Let's see if there's anything else. No, that pretty well covers it. Okay, I'm just going to click calculate for a straight header. If we wanted to calculate for a flared header, we'd have to make sure that we have whatever we want. Here's the ending diameter. And usually the header degrees is displayed right here. I don't know why it's not displaying right now. It's got a little problem, and I'm going to figure it out. Okay. So anyway, typically a flared header is about 1.5 degrees. So if you enter a certain diameter here and it gives you more than that, you might want to reconsider to get a smaller diameter right here. But I'm using a straight header. Oh, I know why it's doing it. When this is 0, it won't show. If you're going to use the flared header, which is a good idea for engines that rev over 11,000 RPM, you would measure from the piston to the beginning of the pipe and put that number here. Let's say it's 50 millimeters. And then you would click here, calculate for a flared header. And then it'll give you the header length without touching that length out there, the diffuser length, the belly length, and the baffle length. But I'm not going to use the flared header, so I'm going to return that to 0, and I'm going to click right here. Okay. So these are all being read by the program. Sheet 2 is automatically calculating for those 2 cones. And we're going to look and see what our resultant pipe power band is on sheet 3. I'm going to click Autograph. Okay, so it's positioned the power band correctly. The beginning and the end of the power band are significant for bikes like 250cc and above. As you get smaller engined, it will start, you know, like a little 75cc will start about right here. So that'll be the beginning of the power band, and this will be the end of it right here. Okay, from what you can feel when you're riding it. So I like that. You know, it's wide enough. If you have a situation with your gearing and you want to make sure this width is going to be more than what you need from shift to shift, you can use this calculator right here. And if you measure the crank rotations per wheel rotation, you take off your ignition cover You mark the flywheel and you watch how many times it turns as you turn the rear wheel. And you mark where that valve stem is so that you know when you've completed the full turn. While you're making that turn, you're counting the crank. And so in first gear, this is what a YZ125 does. It's almost 29 crank rotations per wheel rotation. And then for each, you switch the gear, you put it in second, you do the same thing again, and you write down the number of crank rotations. You shift into third, you just repeat. Okay. So then over here, it tells me that from first to second, I've got a spread of a little bit over 2,000 RPM. Okay, so if we want that power band to cover each one of these, then we have to make sure it's at least 2,000. This is a small engine. It's 85 cc's. So if we go from here to there, that's 500, that's 1,000, that's 1,500, that's 2,000, 2,250. Okay, so we've got it covered. If I wanted that to be longer, I would make the baffle longer, which you can do manually right here. Any of these you can change manually. You can calculate it automatically. And if you want to double check that, that, like to me, that looks a little bit short, the belly. So I'd want to investigate by putting different numbers here. But the important distance for keeping the top RPM is the distance, is all these three or four numbers added together. So if I increase this by 30 millimeters, I'd want to decrease this by 30 millimeters to keep the distance to the beginning of the baffle the same. And it's always a good idea to just double check that the program did an automatic calculation that's good. You make the change here, you go back to sheet 3, and you click the autograph again, and then you're able to look. If you want to record it, you click right here. This records these numbers right here, and the average power right here in the RPM range. So then you go back to sheet 1, make a change, come back here, click here. It's so-so. Okay, we're going to save it on the second row, click that one, and then you do that a few times, and you're able to look right here and compare them all. And maybe if you want to take notes, you can click right here and you enter. Let's say that what we're changing is the belly length. So I would want to enter in what the belly length is as a note. And then going back to sheet 4, we have this section right here. And this shows you how to create the cone pattern. Okay? If you're going to manually make the pipe yourself, which I hope you will. These diameters are the beginning and the big and the small diameter for each cone section. Plus, add in the thickness of the sheet metal. So if this one is 70, the number right here would be 70.7. And on sheet 2, you can find out what the cone angle for each one is, because it's listed right here. You can enter it, if you're going to design it manually, put the X right here, and then you enter the cone angle right here. But when it's automatically calculating, these numbers are ignored, and this is the number that it's going by. This one, this one, this one. We've got automatic 3 cone for a reed valve, So this is section 1, this is section 2, this is section 3. And you can tell it ends at 38 millimeter diameter, which is right here. So it's going by this little calculator right here. The first cone is 90 millimeters long, the second one 70, the third one 60, and then these are the angles right here. And then the inner diameters. The whole program goes by inner diameters, not outer diameters, because that's where the wave action is. But right here you want to add in the width of the sheet metal. And so then it calculates out right here. This length out here, this length out here, those two added together, the chord, which is the straight line right here, and the angle, which is right here. So with a ruler on some poster paper, you can measure that, put a mark, measure that, put a mark, move the ruler a bit, mark it, move the ruler again, mark it. So you can have a dotted line here, and you know more or less where this curve is supposed to end because of the chord. So then you go a little bit farther, and then you draw in, connecting the dotted lines together on both of these, and then you draw the chord, and where that chord length crosses this curve, you put a mark, and then you draw that line back here. And so then you've got this right here, which you can cut out. You place that on top of the sheet metal. You use the marks a lot to draw around it, and that's your cone pattern ready to cut. You cut inside of the black line of the Marcelot. And then just watch my my videotape. Let me see, where is it? This is one of them.
Hey guys, this is Tuck.
And this is my two-stroke page. And if you're wondering about my age, I've been a health food nut for over 30 years, and that's my picture when I was 48 years old. And I'm 63 right now, and I can still kick your ass, motherfucker. I'm just kidding. You watching this video, you're my friend. Okay. Yeah, that's my page. Bunch of good links. My two-stroke calculators right here. This is my Facebook page, two-stroke tuning modifying. And I think that about covers it. If you have any questions, let me know. Thanks for watching.